Hello everyone. So today's tutorial we will talk about RNNs. I will show you some advanced RNNs architecture like LSDM and GRU, and actually we will see some examples why we need sequential models. And for the future perspective, we will talk. I will claim that. These models are not. These models could be replaced by feed-forward neural networks, but for now, as a learning material, we are still want to we are still want to understand how that works. Okay, so before then, we will talk about word representations. Why using RNNs, naive RNN that Alex has been shown in the lectures, LSTM and GRU. This is the advanced RNN architectures. And I will show you the attention mechanism, how it works, and a few papers from the last few years about the usage of attention mechanism in sequential models. In homeworks, you will have a lot of code and LSTMs that you will code to and you will practice how to code sequential models. Okay, so I know that you are boring, so next homework already will be published in a day or something. Okay?
We are so lucky.
Yeah, I know. Okay, so sequential. Let's start talking about text. So how you work with text. So previously we talked about convolutional neural networks and we work with that are working on pictures. So you are kind of understand how it works, how the pixels represents in how the data, how the pixels are represented, okay, in RGB or other representations, and how you feed it in a neural network and it can learn, okay? So today we will talk about how you work with text. So you are actually not working with word itself, just working with their representations of each word, okay? So the naive or the basic methods to working with text is using bag of words model. Okay, so bag of words model using one-hot encoding. So each word of your vocabulary, you actually build vocabulary, and each word is represented is a huge vector, and actually the word hello, it means that that it's place 4 in this vector. Okay, so you build your vocabulary that consists of a lot of words. Actually, all words that you have in your corpus. Corpus, it's like your text or your data that your bot want to process on, to learn on. Okay, so you create your corpus, create your vocabulary, and then you are counting the number of times that each word appears, okay, and its place. So the index of each word is actually hello. It's the first word in the directional, and it can be appears a lot of times. So the number of appearances actually will be counted here, okay. So this is the basic representation of words, and then we learn these representations. Okay, and then we feed it in our neural network. The second approach, actually it's family of approaches called word embeddings. So word embeddings, we are store each word as a point in a space, okay? And then we represent it by vector of fixed number of dimension, okay? So generally it's 300, okay? So this is actually some vector, fixed vector. Here the vector is not fixed, okay? Because it actually depends on your corpus, okay? So if I I can choose big corpus, and then the vector will be bigger. Okay, so it's one of the problems of this approach. Here it's a fixed number. It's actually vector that fixed have length of generally 300. Okay, and then each word, okay, that we want to encode to these word embeddings have some. It's actually some trajectory to this vector. Okay, so and then for example the may hello could be represented this kind. Okay, yeah.
The second way we can think about it as like having the number, the dimension. The dimension is the number of letters in our language, and by the multiplied by the number of letters we have in the word we use. Understand what I mean?
Yeah.
Instead of having only a small dictionary, like we allow.
No, here.
Yeah.
This is not small dictionary.
Yeah.
Again,
no.
In the contrary, it's a very big dictionary, because here, okay, again, if you have text, okay, you have text that contains a million words, okay, your vocabulary will be very huge, okay. Mm-hmm. The number of it will be sparse but very huge. Do you understand why it will be sparse?
Yeah.
Anyone?
If you have one word.
Yeah, because for yeah, the answer is right. I will repeat. Because if you have the words that they shown only once in all this corpus, okay, so they will be represented by one. So their value is negligible. Okay, you will have a lot of some I don't know. 1,000 words that they are common words in the text, okay, so we use the common words, okay, and the other words they will be represented by one or by two, okay, so it will be very huge, sparse vector.
Yeah, but it sounds
here it will be not sparse, because here you take only you take projection on some fixed length embedding. So here it's more dense. It's more actually it's easiest to learn it. Okay, because sparse presentation is very hard to learn. Okay, because you have the problem with overfitting and the gradient gradient to find the context to find the connections. It's very hard. Questions about it? Okay, let's continue. Okay, so one of the basics or common word embedding model it's skip ground. Okay, so another word is word to vec. I think that some of you heard about it. So word to vec is we're taking words, okay, and translated to vector. Okay, there are a lot of other representations and other word embedding models like sequence to vec, chart to vec. Okay, there are a lot of kinds, but word to vec is one of the common. Okay, so we are taking. So how it's work? So for example, we have here some word and pairs. Okay, so for example, we have this is our source. Okay, the quick brown fox jumps over the lazy dog. So we have here the quick and brown. So and here we have the quick brown. Okay, it's actually we are taking another pair, and here we take another pair. So okay, so as you can see, the quick brown fox jumps over the lazy dog. We have here we are training our pairs to we are training, actually we are converting, we are encoding it to our word to vec. Okay, so we are training all our pairs, and then we will have it's actually a neural network. It's fully connected neural network that train our inputs to represent by vector. Okay, so we do it by pairs. We are fitting pairs of our text, and then we have we got the representation, and then we feed in our neural networks the word to vec of our text, rather than taking the bag of words itself. Is it clear? Questions? Okay, great. So the X is actually an input. Okay, it's one hot representation. Y is our true label. Okay, so nearby the input word, and then it's here I explain. So the network is going to learn statistics from the number of each pairing shown up. Okay, so therefore the probability going to get many training samples. So the Soviet Union pair will be the probability to getting it's more than Soviet Sasquatch. Okay, because this word have context. Okay, questions? Why the probability of getting pair Soviet Union is higher than Soviet Sasquatch?
It doesn't make any sense.
Yes, because many years ago there are this country that it's this name. Okay, and so the probability to get these pairs is bigger than this pair. Okay, this is going to be trained, and then we will get some vector that contains only probabilities of each one. Okay, by some projections. Yeah.
This is for the bag of words model?
No, this is word to vec. No, again, bag of words. It's only taking bag of words. It's only taking our words. Okay, making vocabulary and then counting in each index the number.
Right, but here it's going to output probabilities for pairs of words.
Yeah, here I'm taking these pairs, then I'm training it in my model, and then I'm getting the vector that consists of the probabilities. Okay, so here I based on probabilities. In Vertivoc there are no probabilities; it's only counting.
What I meant is that you count the pairs of each combination
Yeah.
instead of don't embed the words to some
No.
vector like we did with the 300 line vector.
No.
Use the words as they are and you just count the pairs or use the model to somehow.
Yeah, I'm only trained the model to find the probabilities of getting of each of them in my corpus. Okay, so this is Skibram. It's a basic word-to-vec algorithm, word embeddings algorithm. Again, it's fixed input vector, generally 300. Okay. So why using RNNs? So here actually example of some fully connected layer. Yeah. So we have 4 inputs and 3 outputs. Here we have some weights. Okay, so this is it's actually a simple way. But what will actually when we expand the number of inputs, okay, when we increase the number of inputs, what happened to my model? If I give more inputs to my network, the number of parameters increase drastically. Okay, so if you want to, so this is actually one of the problems of feed-forward neural network. Okay, yeah, you understand why? Fully connected neural network, you are when you're adding one input, you're actually adding connections to each output. Yeah. So it's actually when you increase the number of inputs, drastically increase the number of weights of your neural network. Great. This is how fully connected neural network work. Okay. So in the opposite, how does RNN work? Okay, so we give function. Okay, this is our function. So we have x1 in input. Actually, we have function f. Okay, so this is the hidden layer, hidden 0, hidden 1. Here we have out. Okay, so if we have the x2, it actually have the same network. Okay, so h and h tag are vectors with the same dimensions. Okay, so your dimension is not increased when you are feeding a sequence of inputs. Okay? In the contrary to feed-forward neural network. Great. So here we have x2, and then we have x3, etc. Okay? So no matter how long the input-output sequence, we only need the function f. This is our function. And if f's are different, then it becomes a feed-forward neural network. Okay? So the difference between RNNs and feed-forward neural network, that f here is fixed, and there f is not fixed. Or it depends on the number of inputs. Questions on the difference between RNNs and feed-forward neural networks? No questions? Okay. Great. So I assume that you have seen some basic RNN examples. Okay, so different representations of RNNs. Okay, so we can have one input and one output. Okay, we can have one input and many outputs, and we actually may have all these permutations. Okay. So here we can feed the word and expect word. Here we can feed the word and expect sentence. And here we can feed sentence and expect word, or sentence expect sentence. This way or this way. Okay. What the difference between this architecture and this architecture? Latency. Yeah. You're right. As an engineer, you're right. You have the latency, but in the meaning, what actually you have here? Here you have some processing. So you have some data that actually you feeding your data, and you have here some memory element of memory that we learn here. The corpus representation, and then we predict the output. Okay, so I will show in LSTM more of this. And here we only feed the network. Here we have some RNN. So each of them is actually fully connected operations, and then we predict the output. Great. So naive RNN for given function f, we have our output y is function of f and h and x. Okay. So we have here h. H is from the previous step from the previous state. Our current input and our current output, and the h for the next step. Okay. Great. So here we have, we are taking weights of our h and weights of our input, and then we have our function. So this is our function h tag, okay? So yeah, okay. And here we have our y. So our y is actually nonlinearity multiplied by this matrix, okay? And then we're taking, if it's classification problem, we are applying softmax on this one. Okay, so pay attention. We have ignored the biases from this network, but you can expand it. It's the biases. It's the same. It's the same way. Okay. Any questions about the naive RNN? you have seen it in the lectures, but again, if you have some questions, we can talk about it. What the problems that Alex noticed about the basic RNN? No problems.
Exploding gradient.
Exploding gradient. Okay, this is very important word because today my next slides will actually explain how we avoid exploding gradient. Okay. Good. But we will summarize the problems. I will summarize problems of basic RNNs and the advanced RNNs architectures. Great. So problems with RNNs. So when we're dealing with time series, okay, it's tend to forget all the information because actually what we want, we have some sequence. We want that each of state will transfer the information that the important information to the next state. Okay, and the problem that in basic RNNs it tends to forget. Okay, so when there's a distance relationship of unknown length, we wish to have a memory to it. Okay, so we want some mechanism that will act like a memory. Okay, great. So the second problem is vanishing gradient problem. Okay, because if your sequence is very high and you have no clear relationship between between the events, it's your gradients tend to vanishing. Okay, so there are no you cannot find really a relationship between the gradients, the weights, and the inputs. Okay. Any questions about vanishing gradients? Anyone understand what it means?
So we have a multiplication of all the gradients, and then if it's smaller than 1, so and the multiplication it's very fast, it can go to 0. That's why you have
yeah. So vanishing vanishing gradients it actually means that your when you start your backpropagation or when you start to derivate your loss function, okay. So in the when you start to get zeros, okay, or your gradient is very small, it can happen between actually we have a few reasons for it, but it happens because there are no clear relation between the previous layer and the next layer weights. Okay, so then your gradients that you cannot derive then the derivation of your function is very, very small. Okay, then you get zeros, and then you can your update weights by nothing. Okay, so this your loss is not getting smaller, and it means that you're vanishing gradients and you cannot train back. So this problem can happen when your layers have no clear connection. Okay. Great. So now we will start to talk about LSTM. So a little bit about the symbols. So this is neural network. This is point operation, vector transfer, concatenate, and copy. Okay. So the sigmoid layer outputs numbers between 0 and 1. Determine how much each component should be let through. Ping X is going pointwise multiplication. Talking about it. So LSTM. So let's start talking about LSTM. So this is cell. Okay. So in cell we have input X and we have two outputs. Okay. So we have ST. So it's a current state cell, and we have h t minus 1. And we have our y. So in each cell we have output y. Great. So, and here we have ct. Actually, what this cell translate to transfer to this cell, ct minus 1 and ht minus 1. Okay. So let's talk about each of the functions. So ct, it's actually the core idea of this cell is to change slowly with only minor linear interactions. So we want that our change will be slow. Slow change can be we can actually find them and we can derive them. Okay. So it's very easy to for the information to flow along unchanged chains. Okay, so this is actually CT is FT multiple ST minus 1 plus IT multiple ST tilde. Great. So the next one is actually, you see, okay. So this is for get gate. Okay. So we are taking the partition of for get gate multiple our ft. So this is actually the part that's going to flow to the next state. Okay. Great. And here we have input gate. Okay. So here we have sigmoid gate. So it determines how much information go through. Okay, so great. So this is here the sigmoid. Very good. So I don't see. Oh, this is the problem. Okay, this decides what actually information is going to add to the cell state. Okay, so this one is cell state. Okay, so here we have some sophisticated mechanism that determines how many of these informations are going to flow here. In the contrary to RNN, so all information is going to, we want that actually only small amount of information are going to flow to this state. Okay? Because we don't want all information, we only want the significant part. The information that will help us actually some memory. You can thought about if we want some very interesting efficient parts of memory that we have here. Okay, so if we have here, I don't know, some. Let's talk about context on the text. So I want that the words that appear a lot here, I actually will have them here. Okay, so I want if I talked here about war or some, I don't know, so attack or something or some synonyms to it. So I want to deliver this information here. Okay, so I want to take only efficient part of information and to translate to transfer it to my current model. Great. So again, so this part, the red one, okay, is decide what information is going to the cell state. Okay. So output gate controls output gate. This is my output gate. Okay. So here we have our output. So output gate controls what goes into my output. So again, I have here some switches. Okay. So this is a controllable switch. Some switches that are this switch I can determine what is going to be forgotten or what is going to be delivered. Okay. Which part of information? Why sigmoid? Okay. Here we use tangents, tan H non-linearities. Why do you think we use here in tan H or not? Because before then I told you that ReLU is a common non-linearity in neural networks.
So then you will give you exploding gradients, and if you use Technion, then you have the saturation area where it just goes to be 1. Because the hyperbolic tangent is between -1 and 1. So you can get too high of a value for the gradient, for the activation.
Okay, and why? Okay, so I will repeat in my words what you have said. ReLU is actually intuitively ReLU is very simple non-linearity function that works well in convolutional neural networks, and it's very easy to calculate it. Yeah. And it's very when we are talking about a huge amount of weights in our model, we prefer to use it. Okay, but tanh we have in tanh function we have two saturation areas. Okay, and the other actually between this we have part of saturation and we have some part of between them. And it's more smooth. It has more smoothness behavior. Okay, so in this kind of non-linearities, it's better to derive them. Okay, so you prefer in the function that you actually have. You have here very complex functions, okay? You have here a lot of multiplications, so you prefer more smoothness non-linearities for better, actually for better approximate your gradient. Okay, so this is the actually the reason why in RNNs we use only tanh non-linearities and not ReLUs. So yeah. Any questions about tanh?
Because you have to be saturated.
So you're actually asking about if I'm not losing the data by using tanh that we have saturation. No, on the contrary, we actually want the saturation. We want in some cases, in some part of this this flow, to use some switches. Okay, so we prefer we are not going to. It's not the influences of tanh. You're not lose your information. You only can control your gate better. Okay, so tanh give you opportunities of control your gate better. And in practical, in the empirical investigation, says it works better. Okay, so they're not. Look, I can give you some mathematics justification, some why. I can only give you some intuition why it works better. We think that it works. The community thinks that it works better because you have more smoothness behavior. On ReLU you have no smoothness. Okay, you have only in the edge you actually have it's very it's cutting. Okay, so here you have more smoothness behavior. So in smoothness behavior we believe that it works better. That gradient in these parts gradients are actually you can derive them. You can derive this function. But you cannot do it in ReLU. In the saturate, you have no saturation there. Okay. So this is you actually want from a function to have some saturations and some other behavior. So what you do not have in ReLUs. So ReLUs cannot act like switch. Yeah. And here we want switch. Because in some part we actually forgot all our memory, so we can in some part we actually taking nothing from the previous state. Great. Any questions? So each one. Okay, I will try do it more intuitively. So here, okay, let's finish this. So we have here function ft. So this is her function. Here we have other equations of AI. So IT decides what component is going to be updated, while CT provides change contents. Here, CT definition, that updating of our current cell, CT, it's our current cell state. And LT and HT is actually what part of the cell are going to output. So again, I can define, the function can be, the weights could be trained this way, that the part will be negligible, around 0, or it will be the all information from the previous state. Okay, so each of LSTM actually contains 8 times of weight multiplication, of matrix multiplication. Okay, so here you have 8 times, so it's very heavy. Okay, so you have a lot of 8 times of your weights in it's dimensionally of your sum of your fully connected that you fit that you forward from your input. So it's still a lot of computation, and actually it's not going to be reduced. Yes, so it's because your LSTM cell is in each step is actually you're doing the same operations. Okay, so the number of your weight multiplication is actually the number of your each cell state weights. Okay, so the next step you're going to train the same weights. Do you understand it? Again, you have one cell, and actually okay, let's see it here. So if this is our cell, okay, if I want sequence, I want to input to feed a few words that have some relationship between them. So I actually I replicate my cell, and then I feed few inputs like x1, x2, x3, and in each step I multiply one cell. Next step, it will be t in time event t plus 1. I will multiply next cell. Okay, and each cell I will have my output, my h and my st that I will feed in my cell in this current state. Questions? Okay, so the first one was RNN. Like as you see, you have only here for both state. You can have here only age and some non-linearity. So here we actually expanded for it's a more sophisticated mechanism. Have a lot of dependencies, but it gives better results. But it can because it can actually better control the flow of the input to the output. You have more options to control it. Okay. You have more weights. Look at it this way. You can train more weights that actually give your that can control the dependencies of input and the output flow. Depends on your depends on your loss function and on your outputs. Okay, so this is actually my LSTM information flow. So we have current state t minus 1 and multiplied by some inputs that are going from ht minus 1 and xt. This is actually my input, and this is h, the second output of the cell. And here we have tan h that are non-linearity. That are, and then we calculate our ct, ht, and yt. Yt it's the output of the current state, and ct and ht they're actually, this is the function of information that have this cell that we can use it on next cell of the next time iteration. Great, so the next one, the next step will be the same, okay? So, and then it's iterative. So, actually, when we are feed sequence to our LSTM, we have the sequence length. It's actually the numbers of our iterations that LSTM are going to have, okay?
What are those Z's representing? What are the Z's?
That is it's functions. It's a fully valued functions. It's transformations. Okay. Great. So this is LSTM. This is a LSTM. It works better than RNN, naive RNN. By you can feed more. Your sequence may be larger. Okay, so you can fit here sequences like I think that it's working well until 50. Okay, so you can actually feed 50 words and then to predict your output. Okay, and it will actually learn the information of these 50 words by this memory, okay, by this mechanism, and the output of the output of our 15th cell will contain a prediction that based on all this information. So, for example, you can give information. You can feed some text that actually talking about some terrorist attack, okay? And then you can, based on this information, you can predict if the attack has happened or not, only by words that contains in this information, okay? So because it has memory, so you can actually have a memory, and it will find the relation between the words to predict the next word. Great. So here we have GRU. I will not go through the equations, but only in a few words. GRU is like LSTM. It contains less dependencies, okay, by combines some parts. So if in LSTM we have 8 times weight multiplication, here we have only 4 times each weight multiplications. And actually, it's worked in this year. Last year, one of the papers talked about the difference between GRU and LSTM over a lot of tasks, and actually both of them works well. So I can tell you that one works better than another in some tasks. So both of them, there are no clear advantage of each of them. Okay. Okay. So this is actually the difference between them. Again, I prefer not to going deep. So again, this is our feed-forward neural network. Okay, and okay, so we have X. We have some function of non-linearities. So this is our A. So T is our layer. So this is how it works. Okay, and on this, it's our recurrent neural network. So T here is the time step. So for each our F here is fixed, like we talked before. And actually, what the difference it's our X and our H, okay? So this is actually the information from the current state cell. Great. So feed-forward nodal network does not have input at each step, and the feed-forward network has different parameters for each layer, on the contrary of RNN. Great. So applications of LSTM and RNNs, I will show you a few applications. Part of them you will implement it at home for your joy. So this is neural machine translation. So actually, it's again, it's a concept, okay? So neural machine translation is one of the famous tasks that LSTM is working on, okay? So you have here, you actually translate from language to language, okay? So here are, this is from French to English. Here it's words in English. So sorry, okay, I will recite it a little bit. So you have here some decoder that decode your sentences in French, and actually it's using our recurrent neural network. And here we have an encoder that encodes this information to English words. Okay. So this is a neural machine translation. This is first you are encoding for hot code for some word embeddings on or bag of words. Here you use your LSTM to find the connections, and here you encode it again from some latent representing to again to word representation. So it's neural machine translation, one of the famous sequence tasks. So this is sequence-to-sequence chat model. It's actually you have here two parts. The first one is LSTM encoder. So here we feed the words. How are you? Okay. So here we feed it. Here will be my output. So I feed my output to the decoder. Okay. So I remember this sequence. Okay. Take some information from here, and then I take my output, my next input, my decoder input from my output of this network. Great. And here I want to predict I am fine. So this is a typical sequence model. How are you? I am fine. Yeah, or not if I have a homework deployment process. Okay, but first you are training your encoder to getting embedding from actually output that will have that will remember the context from this sequence, and here I will feed it here to my input here to decode it to sentence. Okay. Okay. I want to show you attention mechanism, and we will, yeah, it will be the last for today. So attention mechanism. So why we need attention mechanism and how it works. So attention mechanism is actually it's take-talk. It's when we take to account to our input several time steps, not only one, but you're taking several. So if you want to make one prediction, so it's distributed attention over several hidden states that you have, and just importantly, it accords different weights or degree of importance. So to that input reflected below, the lines of different thickness and color. So some of them actually will be more important, and some of them not. So you actually, in attention mechanism, you helping to your model to learn more important sequence. Okay, by giving him some factorization. So the important will be the non-important will be removed by giving the more minor coefficient, and the most important will actually be emphasized. So attention mechanism could work as an input. Actually, one of the examples of attention mechanism when you're removing the repeating words. Okay? So in every text we have repeating words like the, I, and the other words. That's repeating. These words actually are not have some information about the text. They are only for connective words. Okay, connective words in every language. So these words are not informative for and are not helping us to understand to what is text about it. Okay, so this word we are actually removed, and then it's kind of attention that we give to other words. Okay, so this is actually attention mechanism, and you can use more sophisticated attention mechanism, but attention mechanism help us to emphasize more interesting information that actually can help us to solve our task. Great, thank you. I think it's, yeah.